Okay, so to formally begin our program this afternoon, I'd like to introduce Associate Professor of Systematic Theology, Dr. Martin Hanna, and he is in the Seventh-day Adventist Seminary on the campus of Andrews University. He will do our opening prayer for us at this time.
Thank you. Most of my prayer will be adapted from the chemist's prayer that was first published in 1957. Let us pray. Father in heaven, we thank you so much for this Zoom technology that allows us to meet together even when we are distanced from each other because of this coronavirus pandemic. We thank you even more for the technology of prayer by which we can make contact with you, our Creator. O divine chemist, come into the laboratory of our souls and manage the catalyst of our perspectives. Please neutralize the irritating acids of our selfishness with the basic elements of your love. Let the vapors of your fragrance diffuse through the crystalline lattice of our personalities, distill and dissolve our corroded bonds. Let the molecular vibrations of our lives be energized and stabilized by your peace. Let the bonds uniting the atoms of our existence be strengthened by the joy of the Lord. Now stir into the solution of our lives, stir in a double portion of your love, crystallize in us your beauty, weigh in enough of the salt of your preservation, and put on enough divine pressure to raise our boiling point and purify us by the heat of refining fires. In the mortar of our daily lives, crush the coarser grains of our imperfect understanding under the pestle of your chastening love. With your precision, arrange the structure of our existence into a beautiful pattern and infuse us with the resonance that transforms us. Now, Lord, counteract the corrosive fumes of worldly variables diffusing through the laboratory of our lives. Give us enough of your presence to effectively buffer us against these subtle forces. We thank you for listening to us and hearing us and answering us, Heavenly Father, omniscient and understanding chemist of the laboratory of our souls. Amen. Our next participant will be the Provost of Andrews University, Dr. Kristen Arthur.
Thank you very much, Dr. Hanna, for your words of invocation and prayer. I am honored to be able to welcome all of those who are on this afternoon's webinar, our Andrews students, our guests from other parts of Berrien Springs and Berrien County, for our honored lecturer who we're going to hear from in a few minutes. You know, at Andrews University, we take pride in the fact that we cause our students to grapple with vexing questions, the big questions of our day, such as the meaning and purpose of life, such as the origins of life, this afternoon's lecture. Because at Andrews, we think it's vitally important to nurture the spiritual lives of our students, to nurture the faith development of our students. At Andrews, we believe that our students do not have to leave their faith at the classroom door as they grapple with the intellect and the academics of the day. And similarly, they don't have to leave the intelligence at the church door as they nurture their faith and spiritual development. We believe that faith and academic pursuit go hand in hand. they coexist, and they inform each other. Our faith informs our academic pursuit. Our academic pursuit informs our faith. And so this afternoon, welcome to this great lecture as we grapple with this important question of origin. I hope that you'll find it stimulating and you'll leave at the end of this lecture refreshed and energized, and that your faith will be strengthened. Thank you and welcome.
Thank you, Dr. Arthur. I would like to add my welcome to each of you. As Dean of the College of Arts and Sciences, this is a very exciting event to be hosting, and I'm very appreciative to the Department of Chemistry and Biochemistry for putting this program together. As Dr. Arthur mentioned, the topics of faith and science are exactly what an institution like Andrews University should be dealing with and grappling with and discussing. And it's a great opportunity in a COVID world that has limited so much of our contact, that we are able to connect virtually. And in some ways, our current setting makes these sorts of discussions available to a wider audience. And so today, as you participate in questions and answers, as you contemplate the topics and the connections between faith and history, faith and science, particularly in terms of the history of origins, know that you are joining a community who is also very much interested in these questions, and the ability to connect and to really delve into these subjects is a wonderful thing. So welcome on behalf of the College of Arts and Sciences. Thank you so much for joining us. And we'll turn it over to Dr. Ryan Hayes to introduce our speaker.
All right, it's my pleasure to introduce Dr. James M. Tour into our chemistry seminar. I just got to be honest, I was super excited when I heard that he was going to be here. Number one, we have kind of crossed paths professionally, at least the area that I did my graduate work in, molecular electronics, dealing with organic chemistry and how to put molecules together. This has been a big area that Dr. Tour has made numerous contributions. In fact, he's a prolific organic chemist who knows how to make things, chemical structures that are very intricate, very challenging, very complex. And he and his group have published over 700 papers over the last number of decades. He graduated as a chemistry major back in 1981 and has been a chemist ever since. And so he has done a great amount of work dealing with chemicals and how they behave and how they come together. And so I think his comments on this topic, on the origin of life and what chemists and what scientists know about it, are very pertinent. So I'm very glad that he's able to join us. And I also just want to say, I think he did his PhD in Purdue. That's just down the road from us here. And so he does have some Midwest connections. And I don't want to say a whole lot. You can read more about James Tour just by Googling him and looking on Wikipedia. I thought there was a pretty good article describing Dr. Tour, his work, and some of his comments that he's been making in the public. So it's with great excitement and anticipation and with honor that I want to introduce our main speaker here today. And I want to leave enough time for him to talk. And if you have questions, that you would write them in the Q&A part. And if you have general comments, that's good for the chat part. But if you have an important question that you would like to ask, Dr. Martin Hanna and myself will be moderating the questions and getting those ready for Dr. Tour. So without further ado, Dr. Tour, thank you for joining us. And I'm going to turn the time over to you. Welcome to our chemistry seminar program, and welcome to all of our guests from around the world. Thank you for joining us.
Thank you so much for that introduction, and I appreciate the opportunity to be with you today. It was very kind of you to invite me, and this sort of method of meeting makes the travel actually much easier. So in that way, it's been much easier for me, and I appreciate that. I'm going to talk about the origin of life today. I'm going to share my screen here, bring up some slides. So scientists are clueless on the origin of life. And if at any point you're not seeing slides or something, just let me know. All right. So this just gives a little background on some of the things that I've been involved with. These are companies launched from our research in the past 5 years. And just so that you get an overview of the things we've worked on, DOTS is a company that works on carbon or graphene quantum dots, and that's a public company now. Weebit's also a public company that's it builds computer memory, 2-terminal memory rather than 3-terminal memory based on silicon oxide switches. Zeta Energy is a battery company, and that is located just a little bit south of Houston, about 25 miles south of Houston. Neurocords is a company that is working on the restoration of spinal cords, optic nerves, and peripheral nerves. Texting Tips, that was just some advice that I gave to a friend, and he started a company around it. Roswell Biotechnologies is a company that is planning to do the whole human genome map for $100 in 1 hour, using actually a molecular electronic chip, and they're located in Southern California and doing very well. Rust Patrol is a product that's on the market, and it's able to it's the best rust inhibitor on steel. Really just tremendous, particularly carbon steel. Really works extremely well. Carbon Green Technology is a carbon material that is very good in removing certain ions from water, particularly in mining streams. Xariant is a drug that we use for the treatment of pancreatic cancer, and it is in the trials right now, moving into trials in MD Anderson Cancer Center across the street. LIGC Limited is graphene foams for devices. It's a way to make graphene from carbon films using a laser. Just a CO2 laser is found in any machine shop. And so that's actually probably going to spin off into 5 different companies. It's a very powerful technique. We first published on it in 2014, and now in the literature, there's probably 2 or 3 papers per week coming out on the use of this laser-induced graphene for devices. Universal Matter is a company that was started last year. That's the conversion of anything carbon into graphene. So you could go to universalmatter.com and see a little video on how that works. But in 10 milliseconds, we can convert any carbon material with no solvent into graphene. And I mean any carbon material. And the vast majority of things that you see around you in your world, including you, are made out of carbon. Nanorobotics is a company that we use nanomachines in medicine to drill into cells, either to deliver drugs or to kill the cells. We've killed superbacteria, killed cancer cells, and so we have 2 studies going on at MD Anderson across the street and several other studies going on killing superbacteria. NeuroNew means I haven't named it yet. It doesn't have a name yet, but that's using carbon nanoparticles for traumatic brain injury, stroke, and dementia, and more. That's a company that will start this year. Universal Uptake is just getting going right now. I think that's going to be the name. Again, I don't choose the name. I'm not an officer or director in any of these companies. That's how I can have all of these. I just get them started. Capturing CO2 from flue gas and the storage of diverse gases. And then Universal Echem, Again, this is not sure what the ultimate name is going to be. That's for the electrochemical generation of ammonia, electrochemical generation of hydrogen peroxide, and then also the development of lithium-air batteries, and then just 2 other sort of investment vehicles. So we've been involved in several efforts across a number of different areas, from pharmaceuticals to high-tech materials and aerospace materials and things like that. Okay, so this is going to be a technical lecture, and with intent, no God, gods, or intelligent designer is going to be mentioned. Science is going to be used to critique the scientific research. If I talk about God during the main part of this talk, people will want to dismiss it and say, oh, this is all about God. So I'm not even going to mention God. This is going to be, I'll just use science to critique the science. Then at the end, I'm going to bring in a scriptural perspective, but it'll be obvious. That'll be just at the end. So the scientists among you are going to have to deal with the science as it's presented. All right, so this is a car, and this is not fully all the parts of a car, you know, because some of them you see are obviously still put together. There's still pieces put together. The antenna's still there, but there's a lot of parts there. And I'm not sure how many people that are watching this would be able to put this car back together, even if they had directions. But if you had no directions, think about trying to put this car back together. It'd be kind of hard. But all the parts are clean and nice and all, you know, gathered together in a single room. But what if they were not gathered together in a single room? What if you had to gather them and put the parts of the car together? And mind you, this is much less parts than are needed to make a cell. To make one cell has a lot more parts than this. And imagine if you had to somehow find these or accumulate these. And if they weren't all in one room. What if all of these parts were scattered throughout planet Earth? And you had to find parts. Some would be on top of a mountain, some at the bottom of an ocean, and you got to find the parts and put it back together. Before the parts decompose, by the way. It's kind of hard to think about that. And many people say, well, you know, these things are not limited to Earth. Okay, well, now find it. Find it out there. Find it out there. The parts have been scattered out there, and they happen to come to Earth on meteorites over a period of many, many years. So find the parts, put it back together. It's kind of hard, right? That's what we're up against in Origin of Life. Try to put something together, and now the parts go bad. You know, say a certain part is there on Earth, and you're waiting for other parts to come, and in the meantime, the parts go bad. They rust out and they decompose. Same thing happens to organic molecules. They decompose. They undergo oxidation. If you don't want an oxygen-rich environment, okay, how about a nitrogen-rich environment, ammonia? That'll do other chemical reactions. So these chemicals don't last long. So you got to have them all in the same place, all at the same time, or within a reasonable amount of time, because the parts go bad. It's hard to think about how to make a cell. So what's the origin of life? This is a cell, highly complex. It's got all sorts of organelles and all sorts of features here. And some people say, oh, well, you know, this is a modern cell. Cells weren't that complex. They were more like bacteria. Okay, you think a bacterium is simple? You think a bacterium is simple in structure and in composition and in the coordination of parts? And I'll tell you, one of the problems in Origin of Life is that a lot of the people that work in it will be an expert in one thing. Now, we have the good fortune of having worked in the area of organic synthesis, so we know what it's like to have to build molecules. We don't buy molecules in kits like biologists. We have to make them ab initio. And also we work in this area of nanosystems, where we try to put molecules together to form systems that work. You have both of these tasks within cells. You have to make the basic components if you want to do this from Origin of Life, and you've got to assemble them. Molecules don't care about life. Organisms care about life, but chemistry, on the contrary, is utterly indifferent to life. Without biologically derived entity acting upon them, molecules have never been shown to evolve toward life. Never. Molecules don't evolve. That is a term that has been taken out of biology, and people have thrown it into Origin of Life chemistry. It is utter nonsense. Molecules do not evolve. They don't move toward life. They have no reason to move toward life. They're utterly indifferent to life. Almost every chemical synthesis experiment in Origin of Life can be summed up by a protocol analogous to this. And so people always send me things. Oh, what about this paper on this? Trust me, if it's on the chemical synthesis side, it fits into this paradigm. You purchase some chemicals, generally in high purity, from a chemical company. You mix those chemicals together in water in high concentrations or in a specific order. And with some set of carefully devised conditions, you obtain a mixture of compounds that have a resemblance to one or more of the basic 4 classes of molecules, chemicals needed for life, which are carbohydrates, nucleic acids, amino acids, and lipids. You need all 4 of those for life. But it's not just a single carbohydrate. There's many of them, and then there's polymers of them, which is hard to do. They don't just hook together by themselves. Nucleic acids. Nucleic acids have a nucleobase, and then they're hooked up to a carbohydrate, and then a phosphate, and then you want to hook them together. They don't hook together by themselves. Enzymes do this. There's no easy chemistry to do this. There's no prebiotic chemistry that does this. Amino acids. You got to have about 20 different amino acids, and they're all different, and you've got to have them, you have to have these pieces, and you have to have lipids. The lipids, the amino acids, nucleic acids, and the carbohydrates are all chiral. Chiral meaning that they have a non-superimposable mirror image. There are a number of different isomers. Isomers increases at 2 to the n, where n is the number of stereogenic centers. And so it is really hard to make these even in racemic form, let alone the chirally pure form that you would need for making life. Then they publish a paper making bold assertions about origin of life from these functionless, crude mixtures of stereochemically scrambled intermediates, much like Miller did in 1952, the original Miller-Urey experiment. Things haven't changed much if you think of it fundamentally. The world thought they were right on the verge of solving the origin of life, but it turned out to be much harder than they thought. We are now over 2/3 of a century past that. Think of things that have happened in 2/3 of a century since then. I mean, we have space travel, we have internet connectivity, we have the structure of DNA, we have the entire silicon era. All of that's happened in the last 2/3 of a century, 66, 67 years, 68 years. Nothing's happened since then that has added anything fundamentally to the origin of life problem. Then they engage with the ever-gullible press to dial up the knob of unjustified extrapolations. Then they watch the mesmerized layperson exclaim, "You see, scientists understand how life formed." Then they encourage a generation of science textbooks writers to make colorful, deceptive cartoons of raw chemicals assembling into cells, which then emerge as slithering creatures from a prehistoric pond. The synthesis problem is this: molecules that compose living systems almost always show homochirality. The only ones that don't are very, very simple molecules. When building molecular systems, constant redesigns are needed, which take the synthesis back to step 1. So if you do something wrong, you got to go back to step 1. It's often impossible to remove a moiety once it's been attached. So if a natural system is going along hundreds of millions of years to get to a certain point, and I put a methyl group there, how am I going to get that thing off? Nah, sorry, you can't get it off. You got to go back 400 million years. Okay, I'll go back 400 million years. How do I go back? I don't know how to go back. I don't know why to go back because I don't even know where I'm going towards, so I don't even know that it is a wrong methyl group. And I don't know how to go back because I never kept a laboratory notebook, so I'm lost. Synthetic reactions do not know how to stop their current course of progression or why to stop. There's no targeted goal. They don't know that they're moving toward life. Molecules are indifferent to life. They don't know that they're going in this direction. Time, although claimed to be the savior of abiogenesis, can actually be the enemy. For example, carbohydrates are kinetic products. They undergo caramelization or the Cannizzaro reaction with formaldehyde, which is a presumed prebiotic chemical. The formaldehyde plus the aldehyde will convert the formaldehyde to formic acid, and the aldehyde will reduce to the alcohol. So these things decompose. So even if you have it, it's not going to stay around very long. Prebiotic systems do not have the ability to easily purify structure. To organic chemists, if you can't purify, you're in big trouble because the impurities take up the starting material and gum up the works. They get in the way of all the processes you want to do. Free hydroxyls that are not the hydroxyls you want go adding in there. It's a big problem. Reagent addition order is really important. You can't just add reagents and just in any order you want. Chemistry is very exacting. It's like baking a cake. You can't put in the icing. You know, when you're making the dough. I mean, you got to wait for the icing, and the same thing in chemistry, orders of magnitude more difficult. Parameters of temperature, pressure, solvent, light, no light, pH, atmospheric gases, no gases, have to be carefully controlled to build complex systems. There's no other way around it. If people can't do it, if people can't do this, there's no way this chemistry is happening under a rock somewhere. The mass transfer problem is the killer of all roots, because when if you take a certain material, say you start with a kilo of material, you take that kilo of material, go 20 steps forward. You might have 5 milligrams of material left, and this is in a modern laboratory. Well, go back and make more. You can't, because you didn't keep a laboratory notebook, so you can't go back and make more. So it's a big, big problem. And so every time you run out of material en route to something that you don't even know you're going toward, you're dead. That's it. It kills it, because we don't keep a laboratory notebook. So let me just illustrate this with these nano cars which we make. These are little cars. We build these little motors into them, and these spin if you shine light on them, and they'll spin unidirectionally, and that'll push these nano cars across the surface. Here's the little motor. Here's what they look like. These are very small. These are about 2 nanometers this way by 3 nanometers this way, and you can park about 50,000 of these across the diameter. That's this diameter of a human hair. Here's a nanocar on a surface, and you can see it moving along. So in this synthesis of nanocars, which are very simple compared to a biological system, but at least this is a nanosystem that's put together to do some function. Here's some of the steps that you got to go along to do this. Let's just focus in on one part of it. You know, here you're cooling it to 5 degrees, and you treat with manganese oxide. Then you cool it to -10 to -15. To make this azo species, and that's going to end up adding across this thiocarbonyl at -50, and to give the episulfide. And so we're going to read the procedure here, but you see here, this is at reflux in ethanol, so this is at 80 degrees. This is in reflux in toluene, so this is about 110 degrees. Then you're -10, then -50 degrees, and then this one's at room temperature. This one's at 60. This one's at 130 degrees. What's with all the temperature? Why all the temperature changes? Because you have to do this. If you don't do this, the chemistry doesn't work. You need different reactions for each step. You can't just throw everything together and boom, it forms. It doesn't happen that way. You got to work this way. This is the way the chemistry occurs. All right, and then we build these axles. So just take one step. Just think about the intricacies that's needed just for that one step that I had in the box. To an oven-dried, 3-neck round bottom flask. It has to be dry. With the hydrazone 33 and magnesium sulfate. Hydrazone 33, a certain amount. Magnesium sulfate, a precise amount, was added. Dichloromethane. To this suspension was quickly added manganese oxide at 5 degrees. The reaction flask was immediately immersed and stirred in a cold bath ranging from -15 to -10 for an hour and a half. After this period, the reaction mixture was cooled to -50, then transferred to a Schlenk filtration tube, connected to an oven-dried 3-neck round-bottom flask. The deep purple filtrate that contained the intermediate 36 was collected, and the Schlenk tube was rinsed with pre-cooled dichloromethane. I mean, this is hard stuff. You don't know how to do this. You don't know how to do that. And you have a brain. You have a mind. You don't know how to do this because you're not a trained chemist. Even for a trained chemist, this is hard. This is hard even for a trained chemist. And this procedure is abbreviated so that but a trained chemist knows different things. If I were to have to describe this for an untrained person, there'd be a lot more detail. All of this has to be done to build any complex molecule. You can't just do this under a rock. Then you have to identify it. If you don't know what you have, you don't know what you're going toward. And so you identify it. So we use these tools like NMR that dissect these things. And it's hard to do this and try to figure out these molecular structures. So here's what we have to write to convince the world that we got the structure of that molecule. Here's what we had to write. But this is not it. That was just page 1. Here's page 2 of the characterization. So in order to convince the community that we got what we got, we have to go through all this characterization. So in this one paper on nanocars, there were 281 supplemental pages of characterization data to convince the world that we got what we got. You say, well, nature doesn't use NMR. Yeah, nature uses enzymes at each step to assess molecular structure. If it's not the right structure, there's other enzymes that are called in to chop that stuff up, because if you leave the wrong structure in there, it gums up the works for the next steps. But remember, this is prebiotic. This is before enzymes. Nobody knows how this is done. Everybody's clueless. All right, so when you take a nano car and the first nano car we made, the motor would spin at 1.8 revolutions per hour. All right? But then we learned if we pull out that sulfur ring, these are called Feringa motors, originally designed by Ben Feringa, and then we built these into the nano car. If we go to a 5-member ring now, then it spins at 3 million rotations per second. That's faster than any macroscopic motor. So small changes make a huge difference. Well, how do you do this in nature? How can nature pull out that sulfur? There's no way. Once you've inserted that, you can't extract it. That's it. So if you make something that doesn't work very well, you can't go back and fix it. And in fact, even today, there's no known method to do that. So you had to go back to step 1 in order to make this. You couldn't just take a poorly functioning thing and make it good. No, you had to go back to step 1 all over again. So that was just making the molecules. Nobody knows how to do that. Now you have to assemble them into a working system. A protocell is a self-organized, endogenously ordered spherical collection of lipids proposed as a stepping stone to the origin of life. So this is just a vesicle. If you just take oil and water and shake it up really good, you'll get these little beads, and those can be somewhat analogous to vesicles. Usually you need some higher shear, but you get some. And so people say, well, if you have that, that's essentially a cell. That's the membrane of a cell, the lipid bilayer, but let's look at some of these so-called protocell experiments. They purchase homochiral diacetyl lipids from a chemical company, or they synthesize some stereoscrambled lipids. Sometimes they might use a monoacyl lipid. Then they add those lipids to water and observe a small amount of it to form simple and expected thermodynamically driven assembly of those lipids into a synthetic bilayer vesicle upon agitation. Sometimes the researcher will add other molecules that get engulfed by the vesicles as it forms. And they publish a paper claiming that the synthetic vesicle is a protocell and suggestive of early forms of cellular life. They engage with the media to ramp it up, and the layperson says, oh, they made life. Oh, no, they didn't. Cells are extremely complex. They have, there's the outside of the bilayer is different than the inside. They have lots of things going through. Without things going through, they would never work. You have to allow certain things in and allow other things out. These are proteins that allow things in. These are the carbohydrates. Carbohydrates cover the surface. These are sugars covering the surface. And these are really hard to make. You try to do carbohydrate synthetic chemistry, it is really hard. Protection, deprotection, it's just crazy hard. If you look at carbohydrates, if you just take the carbohydrate, D-pyranose, and you have 6 of these to make the hexamer, you can have over 1 trillion constitutional isomers. If you have the wrong isomer, the cell doesn't work. These are made by enzymes, and not just the original enzymes in the DNA template. These are made by other enzymes that may be functioning from other cells, come in and adjust these things to tune that cell to work. If you mess up the carbohydrate structuring, just get the wrong one, that will shut the cell down. These things, every disorder within a cell has something to do with carbohydrate dysfunction. It's very hard to have to do this. And now the origin of life, people are saying, well, you don't need such complexity. How much complexity do you need? Well, it's been calculated you need at least 256 protein coding genes. You're going to need at least 256 genes to put different proteins to put this thing together. Some people, oh, no, you don't need that. You do. You do, and they just keep saying it's simpler than that. And then the rest happened by evolution. That's a bunch of nonsense. You need some level of function to have a cell, or you don't have a cell. All right, then there's the interactomes, the non-covalent interactions. The non-covalent interactions, covalent means hooked together by a chemical bond. And then there's the non-covalent interactions. These are very important. That's why when a cell is dividing. It takes information, puts it on each side, and then it clamps down and splits apart to make two cells. You don't dehydrate cells and get them rehydrated and get them working again. And the reason for that is the non-covalent interactions are very important for information transfer. It is estimated that the protein-protein interactions, just protein-protein, not protein-nucleic acid, not nucleic acid, just protein-protein interactions in a single yeast cell, a simple cell of a single yeast cell. There are 10 to the 79 billion combinations, 10 to the 79 billion combinations of how those could be arranged. And only a few of those are going to work. Just to show you how big a number that is, the number of elemental particles in the universe is 10 to the 90. By elemental particles, do you mean atoms? Yeah, it could mean that. You want to mean not just atoms, you want it to mean electrons, protons, and neutrons? Okay, that's irrelevant. Whether we're talking of an atom or its 100 different components, it doesn't matter. When you're talking about numbers like this, it doesn't matter. That's 10 to the 90. This is 10 to the 79 billion. This is a crazy, crazy big number. This is a 1 with 79 billion zeros after it. That's the number of combinations, just protein-protein interactions. You get that wrong, information transfer doesn't occur. Information transfer occurs through electrostatic interactions or virtual photons that are traveling at the speed of light. You slosh one electron to the next, to the next. These are really complex within a cell. Most biologists don't even know what I just told you. They don't even know this. Yet they'll be convinced that we figured out the origin of life without even knowing the details of the complexity that's here. All right, origin of life protocell assembly is akin to buying 20 pounds of sliced turkey meat, adding a gallon of turkey broth, warming, sticking a few feathers, and suggesting that a live turkey will eventually come gobbling out if given enough time, or that a proto-turkey or extant turkey has been synthesized. That's what the nonsense is like. You think that you could just throw all this in a cell and it's going to start working? There's this huge complex order to the assembly. You can't make the molecules, but even if you could, you don't know how to put it together. You can't just take all the parts in that car and just throw it in there and it's going to work, right? You need one screw out, it doesn't work. Critical for life is the origin of information, DNA or RNA. The information is primary. The matter that we're talking about, which is all we've talked about so far, is secondary. The information is primary. We don't even know how to get the requisite molecules, let alone the code. How do you hook these together, which is your primary code? There's much more information buried, mind you, in carbohydrates than even in DNA and RNA, in the amount of information that can be stored in sugars. Just by gazillions more information. People think, wow, DNA is amazing. Well, I'm telling you, you could put more information in carbohydrates. So and that's not limited to a single set of DNA. Other enzymes from other DNA are acting upon those carbohydrates to change it. It's amazing. This is just amazing. Try to build a cell, even hypothetically. Okay, assemble a dream team, your smartest people. And I'll give you everything you need. So I'll give you all the components, all your amino acids in homochiral form, all your DNA, all your RNA, whatever you want. I'll give you everything. Now, even if I gave you the 4 classes of chemicals in homochiral form, you wouldn't know how to hook those together. But I'll give you the DNA and the RNA all hooked together. So I'll hook it together. You want enzymes hooked together too? Okay, we'll give you any enzymes you want. So now you even have the enzymes, you have the DNA, you have the RNA. And then you have all the amino acids, everything you want. Now just assemble a cell. Go ahead, do it. You can't. You can't. And you know you can't. You wouldn't even know where to begin. You think you're going to make a vesicle and just inject all of those mixed up chemicals in there and it's going to work? You know better than that. It won't work. So even if you had all of those parts, which you have not got, you've not gotten those because remember, they're spread out. But even if I gave them to you, even if you have all those, you wouldn't know how to put it together. That's how clueless we are. You say, what about synthetic cells? In 2010, Craig Venter's group copied an existing bacterian genome and transplanted it into another cell. So in other words, you take the genome, you copy it, and then you transplant that into a cell. So you take out the existing, it's like you took the computer control chip from one car You buy, and you take it out and you put it in another car. So if my control chip goes bad in my car, and I go to the auto parts store and I buy a new control chip and I stick that in, can I claim that I made that car? I made it. I put in the control chip. No, I copied it. I took a copy of the same chip and I just put it in. This is what the so-called synthetic cells were. The people thought they made cells. They didn't. All right, so this is the type of nonsense that's written for students to read. Life began with little bags, I'm quoting, little bags of garbage, random assortments of molecules doing some crude kind of metabolism. That is stage one. The garbage bags grow and occasionally split into two, and the ones that grow and split fastest win. This is in a book by Regis, which is a science writer from Oxford University Press on What is Life. Well, few origin of life researchers would state it so shamelessly that these are little bags of garbage, but that's precisely what origin of life people have been making, is little bags of garbage. But those little bags of garbage have no more resemblance to living cells than a big bag of garbage resembles a horse. All right, how did life begin? This is written by Nobel laureate Jack Szostak in Nature in 2018. This is in the Innovations In section. And this is to explain to the lay reader, not the experienced origin of life reader, but the lay reader of nature, which is already an elevated, just the common person on the street doesn't read nature. Here's what he said. The early atmosphere had no oxygen. It consisted mainly of nitrogen and carbon dioxide with smaller amounts of hydrogen, water, and methane. Okay, I'm okay with that. So by nitrogen, he probably means N2 and ammonia. Lightning, asteroid impacts, ultraviolet light from the sun acted on the atmosphere to generate hydrogen cyanide, a compound of hydrogen, carbon, and nitrogen. Okay, I'll give him that, even though he doesn't know, but we'll give him that. Raining into volcanic or crater lakes, the cyanide reacted with iron brought up by the waters circulating through the rocks. It's no idea. There's total speculation, but okay, you want that? Fine. The resulting iron cyanide compounds accumulate over time, building up into a concentrated stew of reactive chemicals. Now, mind you, if you're a chemist, you know iron cyanide compounds are not that reactive. That's like a sink for cyanide. Life as we know it requires RNA. Some scientists believe that RNA emerged directly from these reactive chemicals nudged along by dynamic forces in the environment. That is a statement of utter nonsense. Utter nonsense. Nobody knows how RNA could have emerged. Nobody knows what that means. That's not a term used in synthetic chemistry. Nudged along, that's not a term used. We have no idea what that means. Jack Szostak is a Nobel laureate, smart guy, biologist. Nucleotides, the building blocks of RNA, eventually formed. Huh? How'd they do that? Eventually formed, they joined together to make strands of RNA. How'd they join together? Nucleotides don't join together. We don't know any chemistry for doing that without having, say, a DNA synthesizer where you protect, deprotect, block, unblock. This is hard to do. Nobody knows a prebiotic system that's going to easily do this, let alone the code which you need for RNA. And a oligonucleotide is not RNA. A oligonucleotide is just some random sequence. RNA is an exact sequence that has a code. It's like taking a box of letters, and saying, hey, there's your book. You wanted me to write a book for you? Here's your book. That's just a box of random letters. Well, that's your book. No, it's got no information in it. That's the difference between the oligonucleotides and RNA. Once RNA was made, some strands of it became enclosed within tiny vesicles formed by spontaneous assembly of fatty acid lipids in the membranes, creating the first protocells. Again, he has absolutely no idea. RNA was made, some strands of it became enclosed, had to get enclosed in there, and formed by spontaneous assembly of fatty acid lipids into membranes, creating the first protocells. As the membranes incorporated more fatty acids, they grew and divided. At the same time, internal chemical reactions drove replication of the encapsulated DNA. No idea how that would happen. So here's the simple picture that he showed, Innovations In, that he said these are simple sugars. They are not. This is propane trial, 1,2,3 propane trial. This is ethylene glycol. But if somebody wants to say they're sugars, you can't have it both ways. Either this is a double bond or it's not. If it's a single bond, there it is, then you can't have this. You can't say this is a double bond and this is a single bond. These are not simple sugars. These are alcohols. You want to call these cyanide derivatives? What happened to your multiple bonds? You got to have multiple bonds somewhere. Phosphate, and then they made an RNA nucleotide. So heat comes with UV light. Heat and UV light will take these things and form an RNA nucleotide? No, no. And he says this is RNA, ribonucleic acid. This is RNA. That cannot be ribose because there's no stereochemistry. Without stereochemistry, that cannot be ribose. If you want to claim that's a sugar, you left out some bonds, but okay, if that's a sugar, you left out some other atoms, but okay, if you want to claim that's sugar, it can't be claimed to be ribose because it's got no stereochemistry. Here is what, the reason he said that is because Sutherland showed that he could get a nucleotide. He could get a nucleotide, but look at all the steps that he had to go through. Depending on how you count, it's about 12 steps. And these are crazy hard steps, even for experienced chemists. Not under a rock type chemistry. And, but does this look like heat and light will take simple sugars and make this? No. But what he says is that heat and light, so the world goes away. You can take cyanide derivatives, iron cyanide, and you can just take these and form an RNA just by heat and light? No way. You see how it's just not true. So then you go back and you look at some of Sutherland's syntheses. Well, so he wants to take this compound and make this compound. All right? So here's what he's got to do. In this reaction, look what happens. To do this, you get all these other products. So this is what he wants to make. There's the NMR spectrum. Look at all the exactness of what he goes through. And even with all of that, in a clean laboratory, not under a rock, he gets not this, but he gets all of this junk too. Look at all this other stuff. And then you'd say, okay, well, then what he does is he purifies this out and he uses this and he carries it on the next step. No. There's the other thing that they don't talk about, is they will take the mixtures and they'll say, we made what we wanted. Now, we didn't bother purifying it and taking it away from that so that we just bought pure 1,2,3 propane triol, and then we carried that on to the next step. But whoa. You mean you bought that and you carried it on? You didn't carry on what you made? Well, no, that's just a technicality. Well, that's just a technicality. How many syntheses do you think are done that way in an organic laboratory? I mean, you could just buy the final product if you wanted to, and then you want to go ahead and start making these sorts of things and say you made it, and so it's built on a house of cards. The whole thing. You didn't really take that and carry it on. Well, the separation's really hard. Yeah, you bet it's hard, even with your advanced high-pressure liquid chromatography, and you leave it to somehow in a prebiotic earth under a rock or in a cave, it's going to purify? So here's my colleague. My colleague who's not an origin of, he's just a really good synthetic chemist, and he has no horse in this race. But I showed him this article of Sostek. I said, what do you think? He says, this is one of the worst one I have read in a while. Sostek is weaving a story based on pure conjecture and wishful thinking, definitely not worthy of a publication in a journal like Nature. He provides no references for the processes that are well, quote unquote, well understood. He uses the term scientists believe based on no evidence whatsoever. In summary, this article is junk. Again, I didn't write this. I am astonished that he, as a Nobel laureate, can just gloss over chemical details. Are you the only one calling these guys out? That's what he wrote. All right. Look at the exquisite exactness that is put into this chemistry to get these things to go. So when you read this, everything is just exquisite. And then they'll get the compound, and then they say, well, we didn't really use it. We just scaled it up to simplify the handling procedures using normal synthetic organic methods. Well, why didn't you use what you made? Because it was a little blip in your HPLC and you claimed it? Without purifying it or without really using that reaction, then you went ahead and scaled it up another way, or you bought it? That's cheating. Look at this exactness. The preparation of cyanoacetylene on copper 1 was suggested as a way to conveniently prepare and store it for use when needed. Here's how it was made. So what I'm talking about for you non-chemists here, we're just talking about cyanoacetylene. That one compound, to make that one little compound, that one right there, look at what he had to go through. Copper chloride was mixed with potassium chloride to generate the Newland catalyst at 70 degrees centigrade. Then a separately generated source of acetylene gas was prepared from calcium carbide. Where do you get all this calcium carbide? He bought it. Where do you get potassium chloride? He bought it. Where do you get copper 1 chloride? He bought it. This gas was bubbled through a Newland catalyst to prepare acrylonitrile. All right, so he's bubbling this gas through, and that's an unstable compound that needs proper isolation and storage. Acrylonitrile is nasty, which was then treated with KCN, potassium cyanide, for 1 hour. Then 5 equivalents of ammonia as a 13-molar ammonium solution adjusted to pH 9.2 with sodium hydroxide to generate the desired aminopropionitrile. All of the reactions were executed in separate clean vessels. Oh, find that under a rock. And properly isolated prior to proceeding to the next reaction. Yeah, you properly isolated, you properly purified before bringing it on. This is just a sampling of the preparations, okay? And all the other things he made were racemic and not chiral anyway. Then he goes on to even higher level extrapolations that, quote, all the cellular subsystems could have arisen simultaneously through common chemistry. Oh, crazy! This is crazy! You're probably just falling out of your chairs right now. That all cellular subsystems could have arisen simultaneously through common chemistry? Where on earth did you get that statement? That's quoting from Nature Chemistry, one of the highest chemistry journals around. And that has raised the level of supposition from mere molecule types to now complex cellular subsystems? You're going to make a whole cellular subsystem where molecules are working in concert toward a common goal? Give me a break. How close have researchers come to making an artificial cell? Well, in November 2018, there was this article published in Science, which is a top journal. Biologists create the most lifelike artificial cells. I was like, wow, I want to see that. I want to see that with the most lifelike artificial cells. So I go to the original article. Here's the original article. Communication and quorum sensing in non-living mimics of eukaryotic cells. So they're saying they've made non-living mimics, but they're communicating in quorum sensing. Ooh. They took semi-porous microcapsules made of plastics. They're made of plastics from acrylate polymerization containing clay. You put clay in it because clay is positively charged. It'll bind DNA, which is negatively charged. We're prepared using modern microfluidics techniques. So you do this in a fabrication facility. Fabrication facility is like it's like a shop where you build computer chips with all of these different tools. And clays have a high affinity bonding DNA. So when DNA was present, so you take these plastic spheres, you make plastic spheres, you put clay in there, but they're semi-porous. So then you throw in some DNA. The DNA is going to diffuse through the semi-porous membrane and stick to the clay. Okay, all right. Then they buy ribosomes, mRNA, messenger RNA, enzymes, and reagents. These were either purchased or isolated from living things. And then they add the medium. And the expected chemical reactions ensue. You get protein synthesis. And the newly formed proteins then diffuse out and go into other microcapsules. It's just normal diffusion. The microcapsules that are closer to that first one get more because they're near. The ones that are further away get less. And they're calling that quorum sensing. That is just normal diffusion. The ones that are close get more. The ones that are further away get less. If you're standing in a swimming pool and somebody pours in 10 gallons of boiling water, you're going to feel that. But the person on the other side of the swimming pool isn't going to feel that 10 gallons of water getting poured in the opposite corner. Why? Because of diffusion. The chemistry of forming proteins in this way is done all the time in industry, in test tubes. It's done all the time. This is far from the press-hyped claim of gene expression and communication rivaling that of living cells. You can buy a kit to do this. You can buy a kit. You just mix these things in a kit and it does this. This is quorum sensing. This is the most lifelike artificial cells. What that underscores is, yeah, That's the most lifelike, which means you're nowhere close. That's what it means. I just got this a couple of weeks ago. Dear Mr. Tour, this is an email that was sent to me. I meet with a number of men, and I've been showing your videos on how outlandish proofs or anything is. But this article was thrown out there as proof that it could be possible. Could you point me to a critique of this article? It would be of a great help. Thank you. Well, I don't want to do critiques for everybody, but I clicked on this to see what was said. Here's the article. Comes out, researchers solve puzzle of origin of life on Earth. Whoa, they solved it. They did. It says it right there. Researchers solved puzzle of origin of life on Earth. And it's not just in Science Tech Daily. It was in a bunch of other journals, too. It came out. So I went to the article, and I read it. Prebiotic amino acids bind to and stabilize prebiotic fatty acid membranes. Huh? This is a portion of the abstract. He takes a vesicle. And you add certain things, and the organic compounds, some of the organic compounds go in that vesicle and help to stabilize it. They help to stabilize it from high concentrations of magnesium. And that solved the origin of life? Well, that's what was written. So I contacted one of the authors here, and I said, could you help me out here? How did this do this? So I'm not going to comment on that right now because after pushing and pushing, first he said he would comment, and then he learned who I was. He said, I'm not going to talk to you about this. I said, this is, why wouldn't you talk to me about this? So he says, it'll take some time for me to answer your questions. It was very simple questions, but he wanted some time. He said he'll do it this coming weekend. So I'm going to give him the benefit of the doubt. But here's what it is. People take a little idea of trash. It's a trashy idea that they find a little bit of something on a meteorite, or they make a little bit of some scrambled something in a laboratory. And somebody says, oh, so you see that's been made, so I'll build upon that. And that gives it a little more trash. And then I'll build upon that, and I'll build upon that. And all of a sudden, they extrapolate to life. It's all based on a house of cards on top of another house of cards on top of another one. They don't even purify the chemicals going along, but those people don't know it because they haven't read the articles. Or they'll look at the meteorite, and it's all scrambled garbage. And I look at some of the ancient, like 35-year-old, one of the meteorite articles was sent to me by the author of that paper who said he's going to get to me over the weekend. It's a 35-year-old paper. And you look at it, and that was the extraction from the meteorite. Did you watch your chloroform? Did that chloroform have a little bit of a sugar in it to begin with? I mean, did anyone breathe on that chloroform? If anyone breathed on it, that could be where the sugar came from, where the carbohydrate came from. And if you guys didn't breathe it, how about the manufacturer where it came from? Did somebody happen to sneeze in the factory that day when the chloroform was being made? I mean, how scrupulous you got to be to have, I didn't say inscrupulous, how scrupulous you have to be in the care in trying to find a little bit of something on a meteorite when you have Earth where life is ubiquitous. This stuff's hard to do. All right, it's fool's gold. It's fool's gold because if you take chemists were trying to make gold from other elements, and they found that you could take iron, and if you added sulfur to it, you would get what looked like gold. And now they knew it wasn't gold because it didn't have the same ductility, it didn't have the same melting point, but they thought they were getting close. No, you can add sulfur all day to iron, you're never going to get gold. The only way you'll convert iron into gold is you got to change the number of protons, and that's hard to do. You need some nuclear reactor system, and that costs a lot more than gold. And so this is what they're doing. They'll find a little something, and they say, okay, well, why are you bothering us? Let us do our research. We're on the right track. You're not on the right track. You're making fool's gold. This is why it has to stop. In 1775, the French Academy in Paris refused to entertain any further proposals for perpetual motion machines. The devices just didn't work as advertised. The mature science of thermodynamics, which gave us a theoretical account for why the perpetuum mobile schemes failed, lay 100 years in the future. Likewise, origin of life researchers seem sadly adrift, and its inability to advance bears witness of that fact. So I think there's a time for a call. We need a timeout. A change is warranted. The demands addressing the hurdles, such as the origin of life's code, routes to the complex assembly and interactomes that are essential, mass throughput, lots of questions, or some conjectures as to why these things don't need to be addressed. have so-called scientific facts ever been shown to be wrong? Okay, so so-called scientific facts, have they ever been shown to be wrong before? Well, does the universe have a beginning? If prior to the 1960s, lots of science, in the 1950s, the majority of scientists believed the universe had no beginning. It always existed. That scientific fact, quote unquote, fact changed in 1964 with the steady state theory replaced the steady state theory was replaced by the Big Bang theory. Darwinian theory to punctuated equilibrium. The scientific fact changed in 1972. Eldridge and Gould proposed that the degree of gradualism commonly attributed to Charles Darwin is virtually non-existent in the fossil record. So that changed in 1972. Climate change killed off dinosaurs. That scientific quote-unquote fact changed in 1980 when it became due to an asteroid impact. That's the Alvarez hypothesis. Random mutation and natural selection, as suggested by Darwin and taught as fact, are recognized by many evolutionists since the 1990s to be insufficient to account for the complexity of life. These things that people my age learned, that random mutation, natural selection account for life, it's a bunch of nonsense that many evolutionists now feel. That its neutral drift is quantitatively more important in understanding genetic differences between organisms. Just the normal drift change between me and my children and their children and so forth. All right, how long ago did dinosaurs become extinct? Or better to say, how stable is soft tissue? One of these has changed. Scientific fact is being questioned since 2007 when Mary Higbee Schweitzer, a paleontologist at NC State, led the group that discovered the remains of blood cells in dinosaur fossils and later discovered soft tissue remains from Tyrannosaurus rex specimens. In 2015, researchers reported finding structures similar to blood cells and collagen fibers preserved in the bone fossils of 6 Cretaceous dinosaur specimens, which are approximately 75 million years old. 75 million years old, and you're finding blood cells and collagen fibers. That tells us that at least soft tissue hangs around a long, long time, something we never thought about before, or scientists or dinosaurs did not become extinct until more recently. One of the two. One can think of these being thousands of years, tens of thousands of years, maybe 100,000 years, but 75 million years old is hard. It's hard. So these things, so facts, things that are put forward as facts that aren't, are always subject to change. Claims that mislead the patient taxpayer are unhelpful, and the public will eventually distrust scientific claims. Let me see something. Uncorrected or unfounded assertions jeopardize science beyond a singular field, especially since there's mounting distrust of higher education in general. Condescending comments toward the public or student, if they will not embrace our conjectures as facts, will lead to continued division between scientists and non-scientists, which can yield public reluctance to fund our research. We must tell the truth with specificity. If it's a fact, say it. If it's not a fact, say it. Blackballing scientists if they bear legitimate nonconformist views by excluding them from professional societies and academies, withholding their funding or denying them tenure is anti-scientific and will retard the advancement of science. So I'm not one for God of the gaps. As a scientist, I would never say that we will never understand the origin of life. One day, in the distant future, we might understand life's origin and evolution of complex systems. That will not lessen God, but we will see him as all the more magnanimous. But until that time, we can't go on saying that we understand these things. As a scientist, I can never say we will never know. I can't say that. We might know someday, but as of right now, we are clueless. Scientific fact versus the Bible. So now I'm getting away from the science part. Let me talk about scientific fact in the Bible. A scientific fact, water, has 2 hydrogen atoms, 1 oxygen atom. That will be the same throughout the universe, and that will never change. There's never been discordance between scientific facts and statements in the Bible. So there's no need to reconcile them. So-called scientific facts, which are really theories, are constantly changing, even on the order of decades, and certainly on the order of a century. So trying to twist the Bible to fit a scientific theory is a frustrating endeavor. All of those so-called facts that changed were all in the last 60 years. Do not let professors with their bold claims of facts upset you. Theories or conjectures are not facts, but unfortunately and shamefully, many professors themselves do not make the necessary distinction. This leads to the confusion of generations of students and even professors themselves. Many professors are confused because they think that somebody understands that. No, if they really looked into the origin of life, they'd see nobody understands. To the student who's inundated with misinformation, Deuteronomy 13, verses 3 and 4 tells us, you must not listen to the words of that prophet or dreamer. The Lord your God is testing you to find out whether you love him with all your heart and with all your soul. It is the Lord your God you must follow, and him you must revere. Keep his commands and obey him, serve him, and hold fast to him. Many people are dreamers in this, and so much of what's said is just a bunch of storytelling. These are dreamers. You're not to listen to them. The Lord your God is testing you to find out whether you really love him with all your heart and with all your soul. He's testing you. I pray you pass the test. I'm going to close with this, because in a group of this size, this is my last slide, group of this size, I never assume anything for where people are with Jesus Christ. But let me say this about God. He says, even I, am the one who wipes out your transgressions for my own sake, and I will not remember your sins. God invites you. The message of the gospel is come. He invites you. He says, I will forgive your sins for my own sake. What is this for my own sake? I will wipe out your transgressions for my own sake. And I liken it to this. If one of my kids went to jail, I would go and bail them out. And even if they said, Dad, I deserve to be here, I would say, you're my child. You're getting out. We'll deal with that, but I'm not going to leave you here. Some people think that they're not worthy of so gracious a salvation. God said, I'm doing it for my own sake. I love you so much. I'm taking you out of that. Romans 10:9 says this, that if you confess with your mouth that Jesus is Lord and believe in your heart that God raised him from the dead, you will be saved. This is what the scriptures say, salvation, that if we confess with our mouth that Jesus is Lord, that Jesus is Lord, we are sinners that are separated because of our sin. There's nothing we can do to get past that. So God provided a way. He provided a way in his Son. His Son died for our sins on our behalf. That does away with our sins. He rose from the dead, and he's seated at the right hand of his Father. Many people saw him. He was seen by over 500 people at one time. He ate with his disciples. He ate with them. He talked with them. He instructed them. He invited them to feel his hands and his feet. He invited them to stick his finger in the holes in his hands, lest you think it was an imposter acting like Jesus. No, this guy, he still had the holes in his hands from the crucifixion. He still had a hole in his side from where a spear was driven right up into his heart. And he told Thomas, he didn't ask him. He told Thomas, he said, Thomas, stick your hand into the hole in my side. He told him to. So he invited him to stick his hand into a hole in his side and just reach up there and feel that hole. This was really Jesus risen from the dead. We must believe in the resurrection. Now, I'll tell you something. I share with people all the time about Jesus and his resurrection. And I have a 10-minute conversation with them. 15-minute conversation with them. They go from not believing in the resurrection. These are all educated people. I only speak to educated people because that's who I'm around. They go from not believing in the resurrection of Jesus Christ to believing in the resurrection of Jesus Christ in a 15 or 20-minute conversation. These are educated people. How do they go from not believing to believing? They haven't had time to investigate the history of this. I have since then. There's a lot of it. But how can a person go from not believing to believing in a simple, short conversation? These are educated people. These are either undergraduates at Rice or graduate students or postdocs or professors or medical students or medical professors from across the street all the time. Every week I see somebody go from not believing to believing. Somebody receiving the kindness of the Lord Jesus in salvation. How does this done? How do they go from not believing to believing? And I'll tell you, I think it's because the truth of the resurrection is already on your heart. It's already there. The barrier would be way too high for us to believe something so incredible as a resurrection and make that a requirement for salvation if God didn't place the truth of it already there. The truth of the resurrection is already there. Whether you're listening to this live or you listen to the recording of this, I invite you to send me an email if you do not know the Lord. This is not for Christians. This is not for people who already know Jesus. So don't send me an email and say, well, can you meet with me anyway? My answer will be no. This is only for people who do not know the Lord. But you want to hear more. I invite you into a Zoom conversation, just me and you alone. Send me an email to tour@rice.edu, tour@rice.edu, or just Google Jim Tour. My name will come up. You'll find my email. Google me, and I will email me, and I will set up a Zoom conversation. Just me and you will meet. 30 minutes, I will share my story, and in 30 minutes, you will walk out a believer in Jesus Christ, saved. You will. Because I've seen it over and over again. I invite you to do that. And with that, I'm going to close, and I thank you for inviting me. I went a bit over time, but I didn't go over time if you look at the time that you gave me to start. So I stayed within the time that you had allotted to me. Thank you.
Thank you, Professor Tour. That definitely generated a lot of excitement, interest in the chat. We've got some questions. I totally agree. We got to later start with some of the introductions. They were very nice, but you're doing great. Thank you. And for all those who are staying with us, we really appreciate it. So if you have a few more moments, we would like to address some of the questions that have popped up in the Q&A. And one of my colleagues, David Novak, who's a biochemist, has one of the most upvoted questions. So it's a phrase that he has shared with me a few times, and I would like to see if we can, I'll just ask the question. It's many, if not all, chemical reactions in the cell are simultaneously at non-equilibrium states. Is there any research that demonstrates that you can have multiple simultaneous non-equilibrium reactions in a single reaction chamber that's at homeostasis?
No. And also that the amount of energy to keep a cellular system in a non-equilibrium state is enormous. Enormous amount of energy to keep things in a non-equilibrium state. So there are things that I mean, you can see things in nature that are in a non-equilibrium state. So, for example, a hurricane just came through nearby here, and these are things, but it's a very regular pattern. In a cell, you have so many non-equilibria going on, things that are out of equilibrium, but it takes a tremendous amount of energy to keep it there. We have no idea how that is done. We know how many ATP molecules. A lot of this has been calculated recently by Brian Miller, and he's a physical chemist, and he's done a lot of calculations on this, discounting a lot of what Jeremy England had proposed, because it's very hard to have something like a cellular system. I mean, a cell is just utterly, utterly amazing. So the short answer is no. Okay,
our next question was upvoted here. It's a little longer, but I'll try to read it quickly. I don't know if you can see them. In many faith communities, including the Seventh-day Adventist Church, there seems to be deep confusion about the basic definition, goals, and claims of the origin of life research, abiogenesis, and the theory of evolution. Can you address the differences between the ongoing abiogenesis research, which seeks to explain the origin of life, and the theory of evolution, which seeks to explain observable biodiversity only after the emergence of self-replicators? So basically, it sounds like, what's the difference in origin of life?
I got it.
Great.
So, no, I didn't address evolution at all in this talk because I wasn't asked to. I could have. And I have, certainly we see it, evolution is a very slippery term. Evolution can be used for very simple little reactions that you can do all the time in the lab, simple changes in biochemical systems. You can see that it's done all the time in the lab. And I don't like to use the term macroevolution, microevolution, because again, there's these things are not clear where the line of demarcation is. Nor do I like to say that it is impossible to generate a new species, because you can generate a new species. This is done. You see this in nature. So, for example, sometimes plants will double their DNA for some unknown reason. They'll double their DNA. So now you have a new species. So these things are seen. But what you never see is evolution of a complex system. How does one system turn into another? By system, I mean this. Whenever I talk about you never see evolution of a complex system, people will always present to me the immune system. Because the immune system is presented with something, and it morphs and it changes depending on what it's presented with. It's an amazing system. But that immune system never becomes a digestive system, never becomes an auditory system, never becomes an optical system. It remains an immune system. So what I like to talk about is evolution of a complex system, because you have to have system change upon system change upon system change in order to have evolution as we know it. You don't see evolution to generate, for example, change in body plans. It's evolution of a complex system. Not only have we never seen it, there has never even been a proposal on how it could happen. So I'm not saying, hey, show me how this happened. No, just show me how it could happen. Because what I feel when I talk to evolutionists is that they are the greatest storytellers in the world. They say, well, there was a change here and a change here and a change here and a change here, and then this happened. With no detail, no detail. And as soon as you start probing for detail, everything starts withering around the edges. And then you present them with another question, and they'll do just the opposite with another story. They don't even have a system with something that they can describe where you could change a complex system. There's not even that. So and I can present it in that way. So yeah, I just don't see a model. As a chemist, I don't see it. As a chemist, I don't see it. Now, if you want to tell me stories, fine. I can tell you stories about how I went to the North Pole and saw Santa Claus. You can tell stories of whoever you want. But without the chemical backup, it's hard for me to embrace it. I'm not saying we won't have the answer someday. I'm just saying as of today, we don't.
Yeah, I resonate. I think those of us who have been in the lab and have had to struggle with making molecules and simple ones. I built some systems with porphyrins and paralenes, and it was nowhere near a photosynthetic reaction center. And I could see the beauty and the challenge that life has to have a photosynthetic reaction center, which has to be one of the first large systems here on planet Earth. But I digress because we do have a few other questions. I'm going to bring up this next one that's here because I think you addressed it, but maybe you could just, we had someone ask, you seem very animated about people claiming to have abiogenesis absolutely figured out. I have not seen many scientists actually make this claim. There is no agreement at all about a theory of abiogenesis that is claimed to be anything like decisive, right? Any thoughts about that?
Right. But then what is put forward is an image to the world. If you ask the typical person on the street, most people would say, oh yeah, scientists have created life in the lab. Scientists are very close. Because of, I showed you an article. I just showed you an article that came out and says, puzzle was solved for life's origin.
I've seen all of those.
And so, yes, scientists in their papers, they do big origin of life. People do affect big extrapolations like Sostek did in that Nature article. Those are big extrapolations, but he stayed short of saying that we've made life. Yes, but those extrapolations, and then they get turned up a few orders of magnitude when it gets turned into the press. And do these guys ever call that information back? No. And so
No.
the world thinks it's been done, so much so that even scientists in the lab, and scientists don't even know the difference between abiogenesis. I'm saying scientists. I'm not talking about economics professors, although they think they're scientists. Okay, they're scientists. I'm not talking about someone in performing arts. Scientists many times confuse abiogenesis and evolution. They lump the whole thing together. I have sent articles that I've written on abiogenesis to my colleagues in evolutionary biology, and they will respond back, Jim, evolution has been proven. Get off of it. And I'm like, the article wasn't even on that. The whole thing is merged in their minds. And yeah, the most origin of life people that I know will stay short of saying that they've generated life, but their projections and what they'll, and I've got other articles. I just wrote a chapter in this book that was put out by the Discovery Institute, something about the mystery of the origin of life, or it's still a mystery, something like that. I have a chapter in there where I give exact quotes from what people have written in research articles, not press, but research articles, and just dissect it point by point by point. No basis for saying this, no basis for saying this, no basis for saying this. So although they have not said that they created life, they have become very close in suggesting it, such that as soon as it hits the press, people think they did it.
Yeah.
And yeah, I'm animated. You got a problem with that? I'm animated with everything. Yeah. So some scientists are not. Yeah, I'm animated about this thing, but I'll tell you, you get these things and you get people firing at you because you take on the mainstream. Either you go away and suck your thumb or you're going to be animated.
You should come see one of my lectures. We have that in common.
All right.
I'm very animated too at times. Just on that topic real quick, on thinking about life, you talked about obviously all these car parts coming together and how complex. So one thing I've been looking for, I'm going to kind of go off from not from these questions, this is my own. How many chemicals do you think it takes to make the simplest living system? You talked about we got to have all these different groups. Is there a number that is it like 100 chemicals?
No, but by, I don't know what you mean by chemicals. If you want to talk about elements, we have carbon, hydrogen, oxygen, nitrogen, sulfur, selenium, and we probably have, iron. I don't know, maybe.
No, I would say molecules. Molecules.
Yeah. But see, molecules. I don't know what you mean by molecules. There are 4 basic types, but within that, within the carbohydrates, you have several different carbohydrates. And if you want to say only those that are homochiral and not talk about the other ones that other people would have to deal with or that you have to deal with along the way, those are homochiral. Now, when they start hooking together, every one of these carbohydrates structures, like I said, you have 1 trillion combinations just from a single D mannose. Think about this. If you just had a single A base in DNA, A, there's only one way to put that together. That's 6 A's in a row. That's it. If you have 6 D mannoses, there's over 1 trillion ways to put that together because of the different branching that can occur in the anomeric center. Over 1 trillion. So I don't know what you mean by how many different molecules do you need to put together. So I don't even know. I wouldn't even know how to calculate that. It's a lot.
Yeah, I've actually just tried to Google and look to see if anybody, do we even know what we're trying to make? How many organic chemicals are we having to pull together here?
Yeah, but see, the argument, Ryan, is that they'll keep saying, well, a simple cell doesn't need all of those. Okay, great.
Okay, what's the simplest set then?
What does a simple cell need? I mean, I was speaking to an evolutionary biologist just recently, and I said, how many protein coding genes do you think you need? He says, none. I said, none? He says, all you need is maybe RNA, 1 RNA. I said, and how would that 1 RNA make a cell? I don't know, but maybe that's all you need. You see, so you try to define life as something that is not life, and then you make it so simple that, oh yeah, I can put RNA in a lipid bilayer. But it's not life like anything that we know. And what we do know from from the fossil record is that the earliest cells that we can identify, have a complexity that are at least as complex as the simplest cells that we have today. That we know from the fossil record.
Very interesting. Dr. Hanna, did you want to bring up a question?
I'll share one of the questions here that has been getting some attention from those who are watching the questions online in our system. What are your thoughts, Dr. Torr, on Michael Russell's theory of how we move from carbon to carbon dioxide to methane in water connected with a hydrothermal vent? Apparently Russell proposed this theory even before scientists knew that there was such a thing as hydrothermal vents. Do you know about that?
I don't know about Michael Russell, but I've read about hydrothermal vents. Look, hydrothermal vents give you a hot temperature and you have carbon. But this doesn't address any of the problems. This falls in. So how did the molecules get made? Hydrothermal vent just gives you thermal, so you have a high temperature, you have some salt there. A lot of these reactions you got to cool, and molecules are going to fall apart at these temperatures. Biological molecules fall apart when you put them near a hydrothermal vent. I mean, these things don't hold up a lot of times. So it doesn't address any of the problems that I put forward on just the basic chemicals, nor does it address any of the assembly problems. None of them are addressed. He's just trying to put out there a few more things of, okay, here's a hot zone. It goes from a hydrothermal vent then to a cold zone, then back to a hot zone. That means this is just changing to temperature and concentration gradients and throwing up some chemicals from the earth. But these are all simple chemicals that don't do it. If you could do this easily, I'll tell you, it'd be done in the lab. If a hydrothermal vent could do this, we'd have done this in the lab by now.
Yeah.
So I don't think much of it.
The next question that comes up says that many, if not all, chemical reactions in the cell are simultaneously at non-equilibrium states.
Oh,
that was already asked.
Yeah, that was Dr. Novak's.
Okay.
Yeah, we already got that. People are asking for access to PowerPoints, but I think we're just going to make this video, not necessarily public available. You have a lot of talks that are already out there. What would you say to somebody, Dr. Torr, if they wanted to have more information?
I mean, you can watch the video. I mean, this is going to go out and this is going to be there in perpetuity. In fact, I told you I'd like a copy of this for my own Dr. James tour. I'll put it up on my YouTube site. It'll be out there for everybody to see. And I think that's great to put it out there for everybody to see. But you'll get a lot more information than this if you just get that book that just came out 2020 by the Discovery Institute. I'm just one of, 15 contributing authors to that, something like that. And I have a lot more in there in that chapter.
Excellent.
And by the way, I have several articles that I've written that are on the free journal Inference. If you just type Inference James Torr, it'll pop up. And that's an online journal, and I've written several articles with a lot more detail than what I just gave you.
Thank you. That's wonderful.
Here's another question that relates to my field of theology. Someone asks, since it's difficult for science to explain the origin of life, why are more Christian scientists not willing to explore the option of intelligent design? Why is that such a hard sell?
Well, I don't know. I never mentioned intelligent design in this whole thing. And the reason I don't speak about intelligent design is because I don't have a way to measure that. And I'm sympathetic to the arguments, but as a scientist, I hold myself to the same standards that I hold my colleagues. How did you measure that? On what basis can you say that? There is no chemical tool to measure intelligent design. I don't have a tool for that. So I can't, I don't go saying that. Now, by my faith, I believe that God created the heavens and the earth and all that is in them. That he did. And the details of that, I don't know. But I know to the extent that is written in the book of Genesis on how he did that. But that's what I know. But as far as a scientist, what I can say, I can't put that forward. So So I don't know what goes on in the minds of other scientists, but I can tell you most of it, in my opinion, most of it is that they're busy with other things. This is not even on their plate. I mean, until a few years ago, I never started even thinking about this. It was that I heard some things at a meeting, and I got all riled up and upset about crazy claims, and I wrote my first article on Origin of Life, and it's propagated from there. And then people have gotten upset with me, which I thought was without scientific merit, and so then I had to write more to defend what I had written. But most of them don't even engage in this. They don't even think about this. They think, evolution, it's all worked out. Origin of life, you kind of know from the foremost reaction, formaldehyde, boom, you got all your carbohydrates, and it went from there. And so they don't even think about it, is my guess.
Thank you.
Okay.
That's it for me, Ryan. Back to you.
Yeah. How much time do you have, Dr. Tour?
Well, let's try to wrap it up, okay?
Yeah. Boy, there's a lot of questions I would love to ask you as well. There's some here. Do you know any of the work that's going on with Lee Cronin? I'm trying to think if I know.
Yeah, I know. He and I were on the Incredible podcast recently.
Oh, I think I may have seen you guys have a discussion.
Yeah, I know his work because I studied some of his work to prepare for that podcast talk. And
what are some of the challenges that are that you would? How would you comment on his work and some of the challenges to their approach?
He's nowhere close to life. Absolutely nowhere close. He's got some autocatalytic reactions that are not random at all. If you look at his experimental setups, they are extremely complex. And he has YouTube videos of his lab with all these different, and even with that, he's just doing an autocatalytic reaction. But what he is doing is he is redefining life, not as we know it with all these different elements that have to have. So you could just Google what is needed for life, and you see all these 7 points that what life does. He's trying to redefine life. What is a simpler life form? Trying to redefine so that he can somehow try to target that. But even what he's shown is just simple autocatalytic reactions, which have been around for 100 years. So I don't think a whole lot of it. What's bothered Christians about it is that when I had this discussion with him on that podcast, is that it bothers Christians that I didn't draw blood, that I didn't stick anybody's nose in the comments that they had made. I would just say things and then let it go, because in the circles in which we deal as scientist to scientist, which it was with Lee, and I really commend Lee that he got on and spoke with me, because most scientists in Origin of Life will not even speak with me. And you try to figure out why that is. You try to figure that out. They'll say, well, Tour's faith has influenced his worldview, and so we can't. I won't mention anything of faith, just right. Science. I mentioned nothing of faith in that podcast, other than when it was asked, was I a believer? That was it. And then I said, emphatically, not just a simple little believer. I believe Jesus Christ is the Son of God, and he's risen physically from the dead. That's what I believe. But other than that, it was pure science. But we don't try to stick anybody's nose in things in these sort of discussions. And so I just addressed them as scientist to scientist. And other than one little comment where I kind of lost myself, I mean, I just addressed him in a cordial manner. That bothered Christians because they felt that I should have drawn blood. And that was the only thing that was going to make them happy.
That doesn't sound very Christian.
Yeah, that's right. And my scientist colleagues who've seen it have said, wow, you really did a great job. You were very respectful. I mean, they really honored that.
Well, I really appreciate your approach and for saying some things. I think it's providing great perspective. I often has felt similar in a lot of ways as a chemist who has tried to make things and to just assume a lot of this just works itself out is very disingenuous about our knowledge. And you are starting to bring that to light, and I really appreciate that. But I think we'll go ahead and wrap things up for today. And we've asked the chair of the chemistry department here, Dr. David Randall, if he would just give a closing thought and to send us out. But I really appreciate what has been said and all the comments, and for people joining us here today. And we'll try to make the video available in our community here. And Dr. Randall, the window is yours.
Yeah. Thank you very much. Dr. Tour, we're really honored for such a someone who's so scientifically distinguished and who's also done a lot of thinking and explaining and having animated discussions about the topic of abiogenesis. So I think you've given us a lot to think about and or remind us of, which is, topics like the chirality of molecules and basically how hard it is to do organic synthesis, right? All these crazy different conditions you have to do. And just putting molecules together it's a really hard job. So we're grateful again for the time you took to share with us some of your latest thoughts on the topic of abiogenesis. I think a lot of the chats that we had come into the panelists were grateful for your time and that we were able to put this talk together. So thank you again for doing this. And that concludes our presentation today. So thank you again.